Hi guys and welcome to another video. So let's get started. In this video, we're gonna start using the IMDB dataset using Keras. Okay, so let's get started. I'm gonna write an example that we have available on the Keras samples. Okay, so let's get started. We're gonna use some of the layers that we haven't seen yet. So let's get started. And also we're gonna use some of the methods. So let's start by using by importing the pre-processing module from Keras. Okay, because we're gonna work with this and we're gonna see more details later. Let's import the module sequential. Okay, from the module we're gonna import the sequential, and let's import some layers right here. I'm gonna import let me see. I'm going to import the dense layer because we're going to deal with classification. I'm going to import the embedding, which we're going to see now. I'm going to import the conv1D, which is a one-dimensional convolutional layer. We're going to import the global max pooling 1D. Okay. So the thing though is that we're gonna import the dataset from IMDB. Okay, the datasets. We're gonna import IMDB, and this dataset, which basically consists of um, reviews of movies and their sentiment. Okay, so this is a sentiment dataset. So we're gonna create some variables right now to set the parameters of this model. So we have the max features, which is the number of words. Okay, let's say I'm gonna use the 5,000 words. We have max length, which is the maximum size of words, and let's put 200. We have batch size. As you can see, the batch size is the number of samples per step. Let's put it 64. We have embedding things. If you guys want to see the examples, if for example you guys should comment down below and you pass the link to those examples so you guys can share, can see for yourself. So we have the embedding dimensions. Usually people use 50 or 100, and some huge models uses 1000 dimensions. I'm gonna use 16. This is very simple task. We have filters, which you will be used in the convolutional layer. Let's use 128. We have kernel size, which is the search space. Let's put it 3. We have hidden size. Let's put it in the hidden size. I'm gonna put it 128. And we have epochs. We're gonna use 2. I think it's enough. So we have those variables. Okay, guys. So let me see if okay. So we have those variables. Let's load the data. So the data is pretty much the same way as in the MNIST. So we're gonna import this data and we're gonna use it. So we're gonna use imdb.load data, and we pass an argument called none words, which will be equal max features. Okay, so this argument will return the number of words which we're gonna use at the maximum. So if I want to print the data, I could do this. Okay, I could print right here. So let's print the length of X string just to give us an idea of how much we are talking about here. So we're gonna do this, and there's the part of pre-processing, which I'm gonna show you guys next. So let's see just how many words or samples we have in this case. So the thing is, if you use this on another data set, you should probably try to figure out the best model to solve this problem. I'm gonna do this later on this course. I'm gonna try different approach to solve uh, problems regarding uh, segment analysis. Okay, so it is taking quite a while to load the data set. Let's wait a little bit to see if it's going to load the data set. I hope so. Okay, I hope that this will load the data set. So yeah, it's taking quite a while. So let's just jump to the normalization pro. So the normalization basically is to take I think I'm gonna iterate over this. I'm gonna use a for loop. Let's go sample in Xtrain just to show you guys the structure of each sample. So basically, I'm gonna pass, which I'm gonna show here, are indexes. Okay, so the thing is, we're gonna use the embedding layer. So the embedding layer takes an index and convert this to a fixed length vector. So yeah, I have a syntax error. I forgot to put in a. So let's come back and fix that. So the thing is, we're gonna take this indexes and convert it to a fixed length vector, which is called embedding. So you guys can see I should just print the first 10. So I'm gonna use the range function, and I'm gonna print string sample index. Yeah, I think that would do the work. So let's print the first 10 samples, and I'm gonna see. You guys will see that we have these vectors which have different sizes, and the convolutional layer doesn't accept variant size vectors. They have to be consistent. Okay, if you want to work with variant length, we need to work with recurrent neural networks. So we need to normalize this. So as you guys can see, we have different sizes. So each vector is a list of indexes. As you guys can see, we have this is index. We have each number corresponds to a word. Okay, so if you know the index of each word, that will be the word itself. So we have this data. So we need to normalize it, and to normalize it, we're gonna use the padding feature. So okay, so we're gonna use Xtrain. We're gonna assign it again, and we use the sequence dot pad sequences. Actually, let's pass the source, which is Xtrain. We're gonna pass the max line argument, which is gonna be equal max line. So we have this. If you guys could see, we have max line which is equal 200. And if we do this, if we run this, we're gonna see that we have changed the source. All samples now have 200, the length 200. That is because, as I said before, we're gonna work with convolutional neural networks, and they need to receive a fixed size vector. So as you guys can see, we have the 0, 0, 0, 0. This is because we instead of when we have a vector which is less than 200, we're gonna put a pause. Actually, a pause. What's the name? We're gonna concatenate zeros. Okay, which means that we don't have in a word, and this is usually pause is actually I forgot the name, but you could change the order. So we're gonna take this 200, which is good enough. Okay, I think we have seen how the data is. So now we're gonna build the model. So to build the model, I'm gonna build the model. We're gonna use a model equal I'm gonna put this over here. Model equals sequential. Okay. And let's add the conv1d layer. Conv1d. And the conv1d, actually the first layer is an embedding. I was forgetting that. So the embedding which will receive the max number of words. Okay, max features, which is the maximum number of words, the embedding dimensions. Okay. And the input length. The input length tells us the size of each sentence, which will be equal to the max length. So if we pass this, we're gonna see that we have which the max length is actually 200. So yeah, each sentence will have the size 200. Let's add another layer. So we have the embedding, which will take, as I said before, the index and convert that to a fixed size vector. We're gonna add a conv1d, and we're gonna pass the arguments for this layer, which are the filters and the kernel size. We're gonna use the padding, which is gonna use valid. The code that I'm writing right here is the same code that you guys can find on the samples on for Keras. Okay, so the thing is, if you check out the Keras documentation, the Keras samples, you guys will see that we have this example right there. I can recommend you guys should check out the Keras examples to learn more about the API of Keras. So we have this, okay. We have the embedding, the convolution 1D, and the global max pooling, which will take that. We need to pass we don't need the flatten layer in this case because this will be in one dimension and will work great. Just works for the dense layer, which we have one output, which will be a number 0 or 1. Okay. And the activation function for this layer will be the sigmoid activation function, which is it's very simple. It's a very simple activation function. Let's compile the model. We're gonna use the atom. Let's use the SGD, the stochastic gradient descent, just to change a little bit. The last will be the binary cross entropy because we are dealing with binary classification. But the mean squared error would work as well. So let's use the metrics accuracy. So we have the model compiled. Let me see if I'm not forgetting anything. So we should definitely now call model.fit. Let's pass xtrain, which was normalized. Ytrain. The ytrain is actually already normalized because it's either 1 or 0. The batch size is gonna be equal batch size, and the epochs will be equal epochs. And we should pass, before not pass the validation dataset, you could usually pass the validation dataset without a problem. So let's run this, and we should be able to see the training menu or details starting. I'm gonna see how long this video is. Okay, 30 minutes. So okay, so let's see. It could take a while. So let's refresh what we did here. So we got these variables, which are the parameters or the details of this model. Okay, we have some details over here. I didn't add the hidden size, the hidden layer, so this is not needed because it didn't add a hidden layer. So we have that I forgot in R right here, entropy. I forgot in R, so let's put it. So as you guys can see, to build this model using Keras, it's very simple. Doing the same thing using TensorFlow would take quite a while, to be honest. So as you can see, we have the epoch and we have the menu starting. We have the accuracy, which is right here. Is saying 50%, and each epoch would take about 1 minute to train. So the accuracy is not improving, which could be caused by the lack of the hidden layer. So I'm gonna add a hidden layer right here. We're gonna add this hidden layer because this hidden layer will help our model capture more. Let's put a 128 activation function. Okay, activation. Let's use it, the relu activation function, shall we? So let's run, and now because we have this dense layer, we should be able to get a higher accuracy right away on the training process. So let's see. I think that says a lot. And if you're gonna use this for a huge project using millions, or actually I think that's a data set with Twitter tweets sentiment analysis, which has over 10 million tokens or actual sentences to train on, and I didn't try it yet, but I think if you guys want to check out this data set, it's huge. It would probably take a while to train on a CPU, but I think it's worthwhile. So let's see how this works, how this goes. So let's just train for 2 epochs. I want to see how good this model will be, because we are in 49% right now, and the loss isn't improving at all. So yeah, I think I have to try to change the parameters. Let's see. Let's see. I'm gonna try to change the parameters. Yeah, we are stuck in. We are stuck in the 50% accuracy, which doesn't tell much about how the model is behaving. So let's see after 2 epochs how good the model will be. Okay, so 51%. So the thing is, we don't have a very good model. I'm gonna try to see what I could do. To do that, I'm gonna decrease the number of each sentence to 100 words, and I'm gonna increase the number of better dimensions to 32. That would be would result in a better model, because we have now a smaller sentence to extract features, and we have a larger, better dimension. But I think 32 is good enough to extract to put more info in each word. So let's see how long it would take to run this. So the thing is that I'm stuck in the 60. Yeah, I think I know the problem, guys. So we are using the stochastic gradient descent, which is a optimizer which is widely known, but I'm gonna use Atom because Atom I think would be better. Let's check out. Okay, so we have done this twice by now, and we've seen that we didn't improve the model at all. So if I run this using Atom, I think, or better, I hope that this model will perform better. So we are reaching, yeah, that was the problem, guys. You guys can see we are now reaching about 65%, 66, 67. We are reaching about 70%, and the model is so let's just let's just decrease the number of embedding dimensions to 16, okay, which will speed up the training because we have smaller vectors. The computation will be much faster. We're gonna gain a speed up, which will help us train this model faster. So I'm gonna show you guys how the optimizer affects the performance overall. If you guys notice, if you use stochastic gradient descent, the optimizer, we're gonna lose. We actually are stuck because when the optimizer finds the local minima, is gonna be stuck. So I think using that is much better. Okay, so let's see. Each epoch would take about 25 or 26 seconds to run. So this model would be, I think this model would be able to produce good results at the second epoch. So let's wait a little bit. We have 72%, 70. We are in 80%, 87. Let's see if we could reach 90%. So 90% will be good enough for real world applications. But some people are obsessed with precision. I think I would probably use some model if I had 95% of accuracy. So yeah, we run 2 epochs. We are stuck in 87. I want more precision because 87 is good, but it's not good enough yet. So let's run for 5 epochs, which again, the thing is that this model will train very very fast because we are using the one dimensional convolution layer. If I could use the dense layer right here right away, and that would probably do the work, but I'm not going to do that now. I'm going to do that in another video. We're going to explore how using fully connected layers do this kind of work dealing with embedding. So we're going to talk about more embeddings. I have a playlist on the channel about talking about embeddings. Okay, talking about ortho vectors. So yeah, the loss is decreasing fast, very quickly. The accuracy is if I think we're gonna reach 80% in the first epoch, maybe 87 or 89 in the second epoch, and maybe 92 or 93 in the third epoch. So I think we are in the right path to reach a good model. So if you guys take a look over here, all these parameters we can change. Okay, if we could change the filters, if we're gonna extract more a more precise or more complex feature extractor, we could use more filters. Okay, we could increase the kernel size, we could increase the embedding dimensions, we could use the number of words that would, all those features we could change and see for yourself how the model does. So I recommend you guys to play around with these parameters. Again, I'm using the example in which you guys can find on the GitHub repository. So you guys want us link to that, you guys could comment down below, and I will give you the link to this example specifically. So let's see how the model it's doing. So you guys can see in the fifth epoch we are reaching over 97% accuracy. So that is a model that you want to work with. 97% is good enough for almost its precision. It's good enough for to trust the model. So you could trust that this model is able to do a good work. Of course, we're not considering that this model would probably overfitting, so we're not taking that into consideration. But if you consider that, you could just use dropout, and that's what been minimized. So thank you guys for watching this video. I know it's a long video, but I think it's worthwhile watching this video. If you guys like this video, you guys could subscribe and leave a like it. Hit the bell to receive my latest videos, and see you guys next time.